All right. Welcome back to Qualcomm lecture series. This is the third talk in the series, and today's talk is by Arun Rangaswamy. Arun's primary research interest is in compilers. His doctoral thesis was on compilers, on optimizing energy, and in the industry he has worked on compilers and libraries for optimizing for performance as well as code sizes, targeting both CPUs as well as GPUs. I know Arun from our PhD days. He used to sit in the adjacent lab. I know him as a very sincere and hardworking person. So welcome, Arun. Over to you.
Thank you very much, Rupesh, for this opportunity and this nice interaction. So today we'll talk about Superblock scheduling for code sensitive applications. So this is going to be the organization of the talk. So uh, we'll first start with motivation, and then we'll go with an overview of Superblock scheduling. After that, we'll see what constraints make what constraints posed by embedded applications make this challenging. Uh, and then we'll see how we have implemented in LLVM and then share our results. We'll also see the limitations of the current implementation and look at the scope for improvement. So, so um, load latency and branch penalty limit performance in order CPUs that many of us may already be aware of that. And often many applications have very small basic blocks, which means that the instruction scheduler may not be able to hide load latency. And it also means that we may have to pay branch penalty often if the basic block layout is poor. So for instance, take an example of this piece of code, um, where first we load from an address into register R0, and then if R0 is not equal to 0, then we go to a label, and then we have a fall through which has unrelated computation. So after that, we again have another conditional branch. So so in this scenario, we can see that the load and the value that is loaded from the memory is immediately used as by the next instruction. So that means that there is very limited scope for scheduling. So this is a problem. In this problem is more uh, there in order CPUs with because the hardware may not be able to do much to hide these kind of latencies. So we can also yeah. So for instance, another thing is that if the fall through path is not taken, I mean if we often have to go to the label, then we are also paying the branch penalty, because in pipeline process, it is often the case that taken branches have a higher penalty in order due to, because we have to flush the pipeline and all. So we can see that here we both load latency and taken branch penalties will severely limit performance in order CPUs. And I mean, if we are considering embedded systems, we may not have out of order process which can do I mean we may not often have out of order CPUs which can do dynamic scheduling. um, so this is this is what I wanted to show in this slide. So if at any point, if there is anything that is not clear or you're not convinced about anything, then please feel free to interrupt. Okay. Okay, so how, what Superblock scheduling has to offer? So so before that, let's define what we'll go with some terminologies. So uh, in this control flow graph, assume that can someone tell me which is the most frequently taken path in this control flow graph? See, in this graph, edges are annotated with I mean, for instance, we have a
Arun,
nine.
someone is asking to go back to previous slide, Arun.
Okay, thanks, Sushim. Yeah. Yes.
Afrin, you have any specific doubt here, or do you want to repeat, Arun, what he said? Arun, could you please repeat this slide? Yeah, can briefly repeat this slide.
Yeah,
Someone is
sure.
asking.
Thanks, Yushim. Yeah. So suppose, assume that we have this instruction sequence where so we can see, assume that the basic block starts with this a basic block starts with this first instruction, that is load. We are loading from an address and into register R0, and in the second instruction, if we are checking if R0 is not equal to 0, we go to a target called label. In this fall through, uh, we have some unrelated computation, and then again we have some um, branch, that conditional branch that terminates the fall through basic block. So we can see that the first basic block has only 2 instructions, and we can a conventional basic block scheduler can't do anything to hide this latency, because there is no instruction that it can insert between these 2 instructions to hide the load latency. Assume that load has a multi-cycle latency, like three or 4 cycle latency. Then here there'll be a 3 cycle load use penalty here. So there is nothing that the as basic block scheduler can do. If we also assume that this label, the from this basic block we often branch to label, then we are also taking the taken branch penalty, which will also be significant if this kind of code gets executed very often. So this is where in situations like this, the Superblock scheduler can help. So that's the point I wanted to make: the significance of um, load use penalty and taken branch penalty. Is there any question? Okay, I'll move ahead and let's see what Superblock scheduler can offer. So consider this control flow graph where edges are annotated with the frequency with which that particular edge is taken. For instance, we have in this control flow graph, we have an edge from BB0 to BB3 with a 94 percentage annotation. That means that this edge BB0 BB3 is taken 94 percentage of the time, as and when compared to this edge BB0 BB1, which is taken only for 6 percentage of time. So can someone tell what is the what is the most frequently executed path in this, as far as this control flow graph is concerned? A sequence of basic blocks. Okay, so we, as we can see from this control flow graph, the sequence BB0, BB3, BB4 is executed very frequently, like 94%, 94%. So we are more likely to encounter the sequence BB0, BB3, BB4 at runtime. So what the Superblock scheduler does is that it tries to find such frequently a sequence of frequently executed paths. Let's call it a trace. It tries to form traces, and then it places the basic blocks in the traces sequentially. That means that BB3 will be the fall through of BB0, and BB4 will be the fall through of BB3. So it places those basic blocks in the trace sequentially in sequential layout, and then it treats those basic blocks, the instructions in those basic blocks, as if they belong to the same basic block, and then it tries to move instructions around so that there is a higher chance of hiding load penalties, so load latencies. So so this is exactly what a Superblock scheduler does. So by this, we are what have we achieved? So so we are reducing our branch penalty, because we know that most often this sequence BB0, BB3, BB4 is, this sequence is taken at runtime, executed at runtime, so that there won't be any taken branches. So the number of taken branches at runtime is reduced. Second thing is, because we are putting those instructions, we are treating all instructions in these three basic blocks as if they belong to the same basic block. Then we may be able to find instructions to hide load latency. For instance, let's go back to the previous example. Assume that the fall through, this go to label is taken very infrequently. Assume, so in this case, so we have some, if we consider this basic block and the fall through as a super block, then we have some unrelated computation, and we may be able to move those unrelated computation between the load and the use of this load. So here we may be, if we are able to move this unrelated computation between this load and its the conditional branch, then we may be able to hide this load latency. So this is what a Superblock scheduler does. Okay, but obviously, since these instructions, since the instructions in these three basic blocks, in reality, they don't belong to the same basic block. There are some challenges in moving instructions around. So let's see what we have to do in order to move instructions across side entries. By side entry, I mean, for instance, in this trace BB0, BB3, and BB4, we call this BB0 as the entry of the superblock or entry of the trace, and then BB4 as the exit of the trace. So BB3 is a side entry because we have incoming edges from basic blocks like BB1 and BB2 that are not part of the trace. So therefore BB3 is a side entry. It is also a side exit because we can exit from BB3 to out of the trace. Okay, so BB3 here is both a side entry and a side exit. So let's see let's see what we have to ensure in order to make sure that when we move instructions across side entries, we don't violate any there is no illegal movement of instructions. See here, let's assume that I1, I2, I3, I4, I5, they are all a single instruction basic blocks. Okay, assume that they are all single instruction basic blocks and they form the trace. Okay, so if we want to assume that we want to here you can see that I3 is a side entry because we have an incoming edge into I3 from a basic block that is not in the trace. So I6 is not in the trace and we have an incoming edge into I3. So I3 is side entry. Assume that we want to move I1 below this I3, that is after I4. We want to move I1 after I4, between I4 and I5. So what can we move it just like that? So what happens if we simply move I3 below between I4 and I5? Can anyone, do you want to tell why this may be problematic if we move I1 between I4 and I5 just like that? Assume that there is no data dependency violation if we simply move. It's legal. I mean, from a data dependency point of view, it's legal to move I1 between I4 and I5. But will it cause some other problem if we do that?
Arun, in comment there is someone says load hazard.
Okay, so assume, thanks, Sushin. So yeah, let's assume that there is no, let's forget about performance issues now. Let's talk about correctness issues only. So, so what is meant by load hazard? Do they mean, do they mean pipeline stalls or something like that, or something else?
Not detailed yet. There just load hazard was a word here. There.
Okay, so assuming that it is a performance issue, let's rule out performance issues for now. Think about exceptions. What if I1 may raise an exception, may raise a fatal exception? If I1 may raise a fatal exception, then if we move I1 between I4 and I5, then in if in reality if we are taking an off trace path, then we are executing I6, I3, I4, then I1, then I5. So assume that at that time, if I1 raises a fatal exception, then then this behavior is illegal, because in reality, if we had never done any superblock scheduling, then we wouldn't have encountered this situation at all. That is, we are executing I1 speculatively. So this, therefore we simply cannot move instructions below side entries. So what we have to do is, um, we have to uh, do like this. We have to make sure that we don't execute any extra instruction on off trace path, particularly extra instructions that may raise exceptions. So what we do is, we just place a copy of I3 and I4, and then we'll directly jump to I5. So we will transform code like this, so that even if we take an off trace path, if we take this path I6, then we will still not be executing I5, whereas in this case we are still able to move I1 between I4 and I5. So is there any is something not clear? If something is not clear, please stop me. Okay, so I'll go ahead. So let's take the second case where we have to move an instruction above a side entry. For instance, in this case, we want to move I5 above I3, that is I5 between I1 and I2. Okay, so can you guess, can you tell, can someone tell me what will be the problem if we simply move I5 between I1 and I2? What happens on an off-trace path if we do that? What are the instructions that we must generate on that we must execute if we take an off-trace path? That is so we must be executing, if we take this path at runtime, then we should be executing I3, I6, I3, I4 and I5. Okay, but if we simply move I5 between I1 and I2, then we on the off-trace path we won't be executing I5 at all. So therefore, which is not correct. So what we do is we just place a copy of I5 and then jump to I3, so that, and then if we do that, then we can move this I5 between I1 and I2. So in this case, whether we take whether we execute the trace or whether we execute the off trace path, our program will be correct. Okay, so please stop me if anything is not clear. Okay, so we saw that okay, we saw what we have to do if we move instruction above or below a side entry, and what happens, what should we do if we move instructions across side exits. For instance, let's assume that we want to move an instruction below a side exit. For instance, we want to move this instruction x equal to y plus z below the side exit b2. Assume that b1, b2, b3 is the trace, and b2 is a side exit here because we are branching to an off trace successor b4. So is it okay if we simply move x equal to y plus z, that instruction, into b3? Wow, is it correct to do that? If we do that, then assume that we take an off trace path b1, b2 and b4, then what will happen? We wouldn't have executed this x equal to y plus z at all. So this will be a problem. So in order to move an instruction below a side exit, what we have to do is we have to place a copy of that instruction on this edge, on the side exit edge, if the value that we compute here, that is this x, if it was live at the entry of the side exit, that is b4, then we have to place a copy of this instruction here at this, on this edge b2 and b4. So if we do that, then we can move this instruction, because even if we take this off trace path b1, b2, b4, we will still be executing this instruction x equal to y plus z on this edge, so there won't be any problem. what if we want to move an instruction above a side exit? For instance, suppose we want to move this instruction uh, x equal to u plus v above this side side exit. Can we move this above this above b2?
No, sir.
Why is that? Yeah, that's a good answer. May I know why that is?
No, sir, I did not revision of it.
Pardon me.
There is a comment in the chat, Arun, generate duplicate side exit.
Yes. Okay. Generate duplicate at side exit. That will also. I mean, that will also be a problem because we want to see in this case, if we take the side exit, we want this definition x equal to y plus z to be available here. If we move this instruction, assume that we move both use x and x equal to u plus v. If we move both of these above this side exit, then we will when we execute this x equal, when we read x here, then we will be reading the value of u plus v and not y plus z. So that's a problem here. So we simply cannot move this. So what we can do is we should avoid moving and such instructions if that computer if that variable, that is x, was live at before entry. So also we should not move an instruction if it may raise a fatal exception when side exit is not taken. So otherwise we will be terminating the program. So which is not correct. So we can see that I mean, we have to be careful when we move instructions above or below side entries and side exits. So in general, moving across side entries is more complex because we have to insert what is called as compensation code in order to make the program correct. So, and it's also the implementation is usually very hard. So in order to overcome these complexities, what Superblock scheduling does is that instead of forming traces, we will form superblocks where superblocks can have only one entry, but they can have multiple exits. So in this program, in this case, you can see that this trace bb0, bb3, bb4, it has multiple entries. bb0 is an entry of the trace, and even bb3 is an entry because we can enter and we can enter into the trace from a block that is outside the trace. That is I mean, we can see bb1, from bb1 we can directly enter bb3 instead of going always through this bb0, which is the beginning of the trace. So what we do is that how do we transform such traces into super blocks where we have single entry and multiple exit properties? How do we preserve that? So we will do that by we'll do that by replicating code. So assume that, for instance, you take this trace which has uh, side entry BB3 and side exits BB1. Okay, which has side entry. This side BB3 is a side entry, and these two are BB1. Okay, and BB1 and BB31 are the exits outside the trace. So how do we transform this code into Superblock which has a single entry and multiple exits? That we do this by duplicating code. For instance, this code is transformed to this code, where in this code you can see that there is only one entry into the trace, and that is BB0, and we only have side exits where, I mean, we can enter this super block only through BB0 and not through any other base block like BB3, for instance here. But actually these two are equivalent, because what we have done is, whenever we have to enter into a side entry, we replicate those blocks. That is, we duplicate starting from the first side entry. We duplicate the entire part of that trace. That is, we duplicate BB3 and BB4. That we are duplicating it here by using a copy of BB3 and copy of BB4, and whatever edges that were going into the side entries will go to the copies. So for instance, in the original program we had an entry from BB1 into BB3, so we will have an entry from BB1 into copy of BB3. Similarly, from BB2 we had an entry into BB3, so similarly like that we will have a copy of instead of BB3 we will jump into the copy of BB3, and this part must be preserved. So we have this copy of BB3 to copy of BB4. That edge will also be preserved. So, and yeah, so this is how we form super blocks from traces. So now we will be able to so since super block has only side exits and no side entry, it is much simpler to deal with. So this is how we simplify trace scheduling problem. But can someone tell me what will be the what is the drawback in doing this? Sure, there is an advantage that we don't have to deal with side entries, but what's the problem, or what is the drawback in doing this? What do we do here? We are replicating code. We are replicating code here. So we can see that BB3 and BB4, the part of the trace that is called tail, starting from the first side entry, that part is duplicated here. Okay, so it may result in it will result in code size increase. So this is going to be a problem for code size constrained scenarios, for instance in embedded systems. So so this is a problem with Superblock scheduling. This is an disadvantage with Superblock scheduling. Okay, so okay, So how do we form traces? So we assume that we have a control flow graph with annotated control flow graph, where each control flow edge is annotated with the frequency with which that particular edge is taken. So what we do is we start with the highest um, we start with a basic block that is executed most frequently, and then we keep choosing the successor of that basic block, which is executed with the highest frequency among all other successors, and then we keep going forward. So for instance, we assume that bb0 is the most frequently executed basic block. So in that case, we'll start with bb0, and then we among these successors of bb0, bb1 and bb3 is executed most frequently, so we'll choose this. And then and from bb3 again we'll choose bb4 because that's the most frequently executed. So this way we will form this trace. So we can also determine a cutoff values for terminating traces. For instance, if we say that if a basic block has a successor which is with, suppose that we have a cutoff frequency of 90 percentage, 90 or 90% probability, then if we ever encounter a basic block which successors but none of them have more than 90 percentage frequency of getting taken, then we will terminate the trace there. So that is essentially what this trace selection does. So okay, what are the problems with Superblock scheduling in embedded applications? So code size will be a very big concern in embedded systems. It's often a big concern in embedded systems, and we simply cannot afford code size
Yeah,
increase.
there was a question in the chat box. So the question was like, if you increases the computation load significantly, do you prune these graphs afterwards?
What Ravi? Sorry.
So someone was asking like, you have increased the computation load significantly. Do you prune these graphs afterwards?
Okay. Computation load means what?
I think I exactly don't know. They may mean that code size probably, but the question was like, do you prune the graphs
Okay.
afterwards?
Okay. Yeah. Okay. Yeah. Code size significantly. Maybe it is possible to do that, but it may not also be possible to do that. So that's a problem with that's a concern in embedded systems. So that's what we are trying to address here. So yes, so as Althea was pointing out, this is a concern that we are increasing code size, and it
So
may
in case of, I don't know if I may add, like in case of like the constrained CPUs, I will more than embedded what I will use the constrained CPUs where there is memory, battery, and other kind of limitations we have, where we need to do more per cycle. So there is always a trade-off which we take between the code size we are bloating up versus the power or the performance gain we will get. So there is a trade-off. We don't get a clean solution every time, but when we get a solution, like we have to give away something if we are gaining performance or saving power, or if we are saving memory, we have to give something on the side of performance. It's a never an absolute win which we get, right, Arun?
Yes, Sushim. Yeah, that's a very nice way to put. Yeah. So it may not. It may in the general case we will have to live with this code size bloat. It may not always be possible to optimize the replicated code away in the general case. In specific cases, it may be possible, but this is a real concern.
Yeah, basically, we look at the performance gain we get versus the code size blot. Is it really worth it? And that's how we make the decision.
Right, right, yes. That's another way to look at, is it truly worth, is the advantage really worth? So another question is trying to understand if avoid side exit. Okay, so if we have to avoid side exit, then uh, we may not be able to find super blocks in most cases. If we avoid side exits also, in that case it's just a straight line piece of code, then there is no reason why they cannot be put inside a same basic block in the first place. So okay, yeah, thanks. Good. Yeah. So okay. So another concern in embedded systems is that embedded processors may not have support for speculation. So as we saw earlier, if we move certain instructions from their original basic blocks, then we may the code itself may become illegal because yeah, because if it raises an exception. So this is also a concern. So this means that we may not be able to move loads or stores in the general case unless we prove that such movement will not result in program termination. So these two are main concerns. So okay, so how do we overcome them? So what what we did is that we terminated traces immediately before side entries, so that we avoid tail duplication altogether. So also since we are dealing with superblock scheduling, we also don't need any fix-up code instruction that is associated with trace scheduling. So in principle, we have avoided code duplication if we do this, and that is basic block duplication if we do this. And second thing is, if we prevent downward motion across side exits, then we can avoid code duplication at side exit edges as well. Okay, this is another restriction. And third restriction is we will avoid low moment of loads and stores across their original basic blocks. So this will mean that our program will always be correct. If we have to relax this restriction, then we have to show that they won't generate exception when the side exit is taken. So with these restrictions, we did an implementation in LLVM. So just to give an overview, a very high level overview. So we just replaced the machine scheduler pass with our superblock scheduler pass. So what this does is, the superblock scheduler pass, it first constructs traces, and then it constructs super blocks from the trace list. By how does it do? It will terminate super blocks before side entries, so that we can avoid tail duplication altogether. And then for each super block, we construct the data dependency graph, and then we schedule. So 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 just to give a hint of the implementation details. So in addition to so we can we said that we have so many restrictions on code movement, right? So we can't move instructions below a side exit. We cannot move loads and stores above their original basic blocks, all these things. So how do we implement this? We just add some dependency edges. So for instance, we add for every instruction we add an edge from that instruction to its to the terminator in its basic block. So we make sure that we don't schedule that instruction after that its terminator. That is, we don't move the instruction below the original basic block. Similarly, we can do all other we can implement all other constraints by adding more edges. Um, so this is how we do it. So I had the ones in this red are exactly those edges that we added. So so what with this, what we were able to do is we could get some 6.6% performance improvement in our benchmarks, and with a very insignificant code size increase, and that even that can be avoided if we do if we account for register pressure. So 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 what we found is that even with so much of restrictions, we could get some meaningful performance gains without increasing the code size too much. So why how this was possible is because often we have code I'll let me okay. So often we have code like we have some, if a condition is satisfied, then go to just give me a moment. I'll see if I can. Okay, so why is it possible to get some improvements? That's because we often have a code which checks for some condition, and if that condition is true, it will jump to some error handling code. So but we know that such erroneous conditions will not occur in the real execution for most of the times. So this is how we will be able to form super blocks. In this case, there won't be any side entries also. So we will often encounter cases like this. So and in these cases, the super block, the conventional basic block scheduler won't be able to do much because of this condition, and then uh, because we have to do scheduling across basic blocks. This simple super block scheduler will be able to handle such conditions and then schedule. So there are so many limitations of this work. So for instance, in our implementation, we didn't model register pressure, and then we didn't also preserve debug information, and also our current implementation is very restrictive because we don't move loads and stores above across their original basic blocks. In particular, movement of loads above their original basic blocks may fetch more benefits. um, so instead of just giving up, we can try to see, for instance, in most cases, it is often safe to move loads from stack addresses or loads from global addresses. Global means global variables. If we are loading from a global variable, then we we are almost sure that it won't be, I mean, we are often sure that that load won't access any illegal memory, because we know that it's a statically allocated location. So it's often safe to move loads from move loads that load from stack memory um, or global locations. Of course, we have to check that the offsets are also legal, offsets are also valid. So such loads can easily be moved across their original basic block. And secondly, um, we can allow download code motion if the result is dead on all off trace paths, or if the value that we compute down is available for use in all off trace paths. So if we do that, then we can move instructions below side exits as well. And another limitation is that the scheduling decisions are based on single issue processor model, but we can easily overcome this. And another thing that we observed was that alias analysis is very important for getting better scheduling, because we have so many memory edges from memory data dependency edges involving memory, and many of them may be are very likely conservative, because we couldn't prove that these loads and stores don't alias. So if we address these issues, then we will be able to get some more benefits even without increasing the code size. So we are working on some of these issues. So these are the two references. So I mean, they are very old. I mean, they are very old papers, but they are still very relevant for our case in a embedded scenario. So
Arun, there is a question, I think, which says like, was the final target a in-order core? So I just told it's in order. We tried on in-order core, and then one follow-up question on that was like, would you say that this idea of mimicking out-of-order execution on in-order cores using compiler support?
Thank you, Pankaj. Yeah, I mean, yes. Rather, I mean, yeah, we can call it that way. This is simply a scheduling problem, just where a scheduler always tries to reorder instructions from, I mean, from the original program order. So we can view it like that, like how Aditya tells.
Yeah, but it's part of it. We are not mimicking the whole out of order thing. Just this part of it, right?
Right.
There is a point around there. Have you looked into Itanium compiler implementation, because there were some similar ideas used there to improve IPC instead of relying on out of order cores? I
Okay.
think, yeah. Go ahead, Arun. Yeah.
Yeah. So no, actually, we didn't look into the Itanium compiler implementations.
Yeah,
No.
thanks for pointing us, because I also knew that we haven't looked into. We'll probably, look into it what they have done. If it is something of our help, we'll, definitely learn from them. Right, Arun?
Yes, Sushim. Yes, thank you. Yeah.
Yeah. Yeah.
So Arun, one question.
We are done, Arun, right?
Hello,
Yes,
Arun, one question.
yes,
Yeah.
yes.
So you have mentioned about this particular way of scheduling super blocks. Uh, just for the sake of uh, the information for the audience, do you mind mentioning some of the other ways in which super blocks could be used in compilers?
Uh, okay. I mean, I'm sorry, Rupesh. I can't. I'm unable to. Uh, I mean, I'm on top of my head. I'm always like Superblocks are for scheduling. Anything else, Rupesh? Do you have in your mind?
Yeah, I was thinking more from the perspective of, for example, uh, now that you have uh, uh, different control flow graph, which is still cohesive in some sense, will that be useful for certain optimizations, which are by default not possible? I mean, rather, I would say that which are little difficult or not natural on a basic block, but turns out to be easy or relatively easy in a super block setting.
Okay.
Yeah. Anyway, that's fine. So Aditya has another question in the chat box.
Uh,
Okay. Can you use superblocks to reduce dependencies seen in heterogeneous execution platforms?
I'm sorry, Alcha. I didn't get this one.
We haven't explored. I don't think we have explored anything in the research.
Yeah. What is dependencies in heterogeneous? Can you be a bit more specific? Yeah, but surely we haven't explored it.
Yeah, we have only explored the superblocks for scheduling purposes, right? Or
Yeah,
nothing else.
yes, Sushi.
If
Okay,
Aditya
okay.
says it, yeah.
No, we have seen we this is only for within a CPU. No, we haven't. No, we haven't tried those scheduling across those boundaries, CPU, GPU, or non-hetero. I mean, heterogeneous boundaries. We haven't explored it. Okay.
Ye-
Okay. Yeah. Okay.
Yes. Yeah, that will be an interesting problem to do, but we have not done it. Yeah.
Right. Yes. Yes, Aditya. Thank you.
Yes.
Right.
Yes. Plus memory coherence will be added challenge. Yes.
That's true.
Yeah.
These
So
are
for us,
generally
what happens is like 6.5% kind of gain becomes a very huge for us in CPU constrained the constrained CPUs. So every performance bit which we can extract increases the battery life. So that's why like I'm not sure how many of you know this, but a lot of times when you see a phone and a phone Pro, quite a few times it is the same silicon and the Pro is some enhanced optimization brought in compiler and some other domain to get a Pro version of it. So a lot of time toolchain creates a lot of value add for existing offering because a hardware spin-off takes quite a considerable time. So a mid-life, a boost to a hardware performance is a lot many times comes from the toolchain.
and Aditya, this part which you are exploring, I think this part is mostly handled by the runtimes. For example, like OpenMP runtime, or like if you, in case you don't have a runtime, then maybe you need to have some kind of customized solution. So this is a like little off area, I would say, from the one which we are addressing here.
So before you answer Aditya's next question, just wanted to check, Aditya, do you mind introducing yourself where are you from, and so that it will be easier for us to put things in context. Because you have been quite interactive since day one, and it
Yeah.
would be very useful for us to know where you are coming from and what your background is.
Rupesh, just wanted to let you know that one of the participants from your previous talks, thanks for arranging these talks. She is not today here, but she's interacting with us on a lot of questions and problem statements.
Oh, that's wonderful.
Yeah,
That's
yeah.
very nice to.
She's from IIT Kanpur, Dr. Swarnendu Biswas student. She
Oh, I
is
see.
interacting with us on some problem statements. She attended the first two lectures.
I see. I see. That's very nice to know.
Hi, can you hear me?
Yes, yes, Aditya.
Okay, hi. Good afternoon, everyone. My name's Aditya. I would say I'm just really interested in architecture, and I've done quite a bit of courses. I've read many papers. In fact, I've written few papers as well, and most probably, I just like to learn more and more about architecture. And the problems that you're describing, I would say these are really interesting problems in embedded systems, but they're really applicable in other domains as well. As I just mentioned, if you look at 10-year trends in architecture, we see that these out-of-order cores have run out of steam. Your Moore's law is dead. Your technology won't scale beyond maybe 2 nanometers, 3 nanometers. I mean, at least I'm hopeful that it will
Yeah,
go, but we don't know it will go or not. So I think
maybe.
we really need to look into these kind of heterogeneous computation platforms. But
Yes, it's good to know that you are from architecture. I have I'll connect to you some maybe somehow one-on-one. I have some queries on architecture or some discussions going on internally which I wanted to know more. Yeah, I'll connect to you some offline. Yeah,
thank you so much. That would be amazing. That would be really nice.
yeah, something on the neuromorphic computing. Yeah, I'll connect to you offline. Yeah.
That is one of my strong interests. Or
Yeah.
did you do background research on me?
No, 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 no. I didn't do background research. We were discussing True North a couple of days back. That's why.
Yeah, True North, Spin Maker, all of these are. I mean, I don't really believe in True North because I think by the time they manufacture True North, they
Yeah,
would be
it's recorded.
too out of age. But yeah, maybe we can discuss offline.
Yeah.
Anyways, it's really nice to hear these lectures and get your perspective on this because it's very difficult to find architecture people in India. I don't know.
Yeah. I'll connect to you. There are very nice people. I'll connect to you. Yeah.
Thank you so much.
Okay, I don't have I mean, I'm not sure. I mean, I don't have that detail with me right now. So,
Okay, that makes sense because the only reason I asked this question is because I know of one example which really mandates that you have to use an in-order core because of a technology constraint. I mean, I don't know what is Qualcomm's planning in this, that they're mandating in-order cores for these hexagon TSPs. But yeah, basically what my feeling is that you have just tried to move the out of order execution requirements in your front end from your hardware to your compiler. I mean, that is the feeling that I get after. I'm not saying it's wrong. It's a really cool idea to actually get more performance, but Itanium struggled with exactly this implementation. Itanium struggle with I mean, they tried to do this, right? They wanted to uh, improve IPC by focusing on superscalar instead of out of order. And nobody bought them. Nobody bought that idea. So I don't know. There are some bells in that direction ringing. I don't know.
Sure, I think this is a very interesting discussion, and I think this will probably take things forward for both the participants as well as the speakers. Uh, any other final questions at this stage? All right, so let's thank Arun for his nice talk on Superblock scheduling. Thanks a lot, Arun.
thank you so much, Rupesh, IT Madras, and Sushim, and our Qualcomm friends for this opportunity. Thank you very much.
Yeah. Next week we'll have a second talk from Arun. And until then, see you. Bye, everyone.
Thank you very much, Arun. It was a really nice presentation. Thanks a lot.
Thank you very much.